So, Nick, we've been talking about time dilation, and hopefully I've convinced you that it's real. Why don't we notice it? Put your pencils down, look up. So, Brian Greene is a professor at Columbia University. You may have seen him if you watch nerdy science shows. He's one of the world experts on Einstein and general relativity. And he put out a bunch of short little videos. Sorry, I didn't see that was blocking the projector. Right around the anniversary of Einstein's general relativity papers. So let's talk a little bit about relativity. How fast does time slow down? And you with me?
When Einstein realized that time elapses more slowly for an object in motion compared to the rate at which it elapses for us here on a stationary clock, he didn't just make a qualitative statement. He made a quantitative statement. He wrote down a formula that tells us how much more slowly time will elapse on that moving object. And if you like equations, the slowdown formula is 1 over the square root of 1 minus v squared over c squared.
And who doesn't like equations? Of course, we all love equations.
V is the speed of the object, c is the speed of light. But if you don't really like formulae,
who would that possibly be, please?
Let me show you that equation in action just through some visual illustrations. So here is a stationary clock with us on Earth. Here's a clock on a spaceship. Now, if the ship is not moving, the two clocks tick off time at exactly the same rate. But now, let's give that spaceship some velocity, 1,000 miles per hour.
So, which one is moving? The spaceship. This would be T0. This would be T. And he's written this software so that this will calculate T0. At 1,000 miles per hour, though,
reasonably.
Is there much of a difference?
Notice that the slowdown, while there, is just too small for us to see it. That's why we don't know about the slowdown at everyday speeds that we can achieve. But let's take this 1,000 miles an hour and kick it up to a much higher velocity. 100 million miles an hour, about 1/6 of the speed of light, fast enough to go around the entire Earth in a single second. There is a slowdown on that clock. If you look really close, you kind of squint, you can kind of see it, but still, even at this very high speed, difficult to see.
But it is there. You can see they don't quite line up anymore.
What a big slowdown. So let's kick up the velocity of the ship even higher. Let's bring it to 600 million miles an hour. The speed of light is about 670 million miles an hour. Now, this speed, the slowdown of time becomes obvious, right? This clock is ticking off time much slower than our clock here on Earth. And just to see it even more starkly, let's bring that speed of the ship even higher. Let's put it at 668 million miles an hour, just below the speed of light. And look at how time is elapsing on the spaceship clock. Very slow compared to the rate at which time elapses on our ordinary clocks here on Earth. And this really illustrates quite wonderfully how we don't know about the slowdown in our bones intuitively because we never achieve speeds anywhere near the speed of light. But if routinely we did travel at speeds near the speed of light, this slowing of time would be obvious to us. This dramatic slowing of time near the speed of light would be intuitive. It would be in our bones.
Back to our notes. So, why don't we notice time dilation in our everyday lives? Look at the time dilation equation. Let's write it out. T equals T0 all over the square root of 1 minus V over C all squared. Write that down. It's on my formula sheet. Yeah, I know, but I want to make a point here. And then circle the square root thingy, the denominator. Okay? This circled section actually has a name. It's called the Lorentz factor. This was actually discovered before Einstein published his paper. A physicist / mathematician named Edward Lorentz, about 5 years before Einstein published his paper, said, look, when I look at the weirdness between a moving object flashing a beam of light and a stationary object flashing a beam of light, I can't explain it, but I can make the numbers match with this. So he figured out that square root of 1 minus v over c all squared was part of it. He just didn't know why. So it's often symbolized, because it shows up in the relativity equation, and we like to abbreviate, with the Greek letter gamma. A Greek letter gamma kind of looks like that. It's sort of like when you draw a fish on its side, but make the fish really skinny and doing a headstand. That's a Greek letter gamma. Gamma in physics is the square root of 1 minus v over c all squared. It's an abbreviation for that Lorentz factor. And so read, you can, if you want to, write the time dilation more simply as that. And I think I gave you both versions on your formula sheet, didn't I? I gave you the long version, but I also know as teenagers you like to abbreviate, and there's good nerd quality because, ooh, it's a Greek letter. I'd like to abbreviate even more with a Greek letter. So if you want to, in your notes, replace writing out the square root with that, I'm fine. But let's look at this. Specifically, let's look at 1 hour of time. So t0 is going to be 1. For each of the following situations, a human walking, so the human is moving, how much slower is time moving for the human walking than for someone at rest? Let's calculate it. What's the speed, Brea, that they gave me for the human walking? So I'm going to go like this. T equals, T0 is 1 all over the square root of 1 minus 2 over, unfortunately, I can't go do you see, what do you see? I have to type in the 3 times 10 to the 8th squared. And I'd like you all to follow me type by type on your calculator. Don't go ahead, but get your calculator out. If I was going to calculate this, I'm going to calculate this the long way. And so, Nick, what I'm going to do is I'm going to do the bracket first. I'm going to go 2 divided by 3, scientific notation button, 8. And if you do that on your calculator right now, you should have 6.6 times 10 to the negative 9. See if you get that. You're typing along and following along with me. What's just outside the bracket? Squared. So hit your x squared answer button. And now you should have 4.4 times 10 to the negative 17. Now what would I do? I guess 1 minus that. So if I go 1 minus answer button, what? Is the answer actually 1? It can't be, because we went 1 minus something. This is the limit, Lena, of how even your good calculators will round off. They won't carry that many sig figs. So I've actually crunched this, but I had to find an online long number calculator. You can find them. People have written software that instead of carrying about a dozen sig figs like your calculator does, they carry it to about 50 sig figs and they'll crunch it for you. But for all intents and purposes, if I'm walking relative to you, is time moving slower for me? Yes, but negligible. My calculator, it's so small, my calculator crashes. So even though technically an hour for a human walking and an hour for a person at rest aren't the same? Realistically, they are. It's so small, we don't have to factor it in. Well, let's go a bit faster. Let's go in a race car. So we're going to do the same calculation we just did, but instead of a 2, what number am I going to put where the 2 is? So let's get out our calculators, because I want to write this out every time. Let's go 70 divided by 3, scientific notation button 8. Do you all have 2.333 times 10 to negative 7? Mud's following along on his calculator. Sorry? You already did it? Oh, okay. And then squared. And you have 5.44 times 10 to negative 14. And then 1 minus answer button. And again, I think we run into the same issue. Too many sig figs for our calculator to track. So is time moving more slowly for a race car driver than for us? Yeah. But Dan, do we take that into account at all? Do we really? No, it's for all intents and purposes, it's negligible. Ooh. What about the SR-71 jet, the fastest jet we've ever designed? Now, the top speed of the SR-71 is classified, but we do have records of it going at least this fast, 1,000 meters per second, 1 kilometer per second. Let's see if they experience a significant amount of time dilation. So instead of a 2, what number am I going to put there? A 1,000. 1,000 divided by 3, scientific notation button 8. Oh, wrong button, Mr. Duke. Scientific notation button 8. Squared. 1 minus that. Uh-oh. Even jet fighter pilots, not an issue. Okay, what else moves faster than a jet fighter? Yeah, but I think the next one, what did I move into next in the column? I said, hey, Earth moves around the sun, which means technically time for us and time for the sun are different. So where the 2 was, let's put the Earth speed relative to the sun. So it's going to be 29,600 divided by 3, scientific notation button 8. Squared. 1 minus that. Oh, hey, I got an answer still. Yes? And I think this is where all of your calculators kick in as well. Now what? We're moving out from the 1 minus. What's the next mathematical operation we need to do? Look at what we wrote. What's the next mathematical operation we need to do? Yeah. Yours says 1? Okay. Yours shouldn't. I'm wondering if I would try retyping it quickly. You might have missed a step. Specifically, you might have maybe missed the square. I'm not sure. Maybe not. It might be how your calculator is set up. Okay. So have patience. We'll get to somewhere where we will get an answer. But what? Yeah. You got. Yeah. You got 1 point, a lot of decimals in the 5?
Yes. I think we could go 1 over.
You can't do the 1 over yet. No, you can't. Okay, first of all, we haven't square rooted yet. I'm not done yet. Okay? All I've done is that step there inside the square root. So now I'm going to hit the square root button on my calculator. This is why I said follow along with me. Answer button. And now if I go 1 divided by answer button, this is the final answer I get. Maybe this is what you were talking about. I get, okay, in my final answer, I get a 1 with, how many zeros? 1, 2, 3, 4, 5, 6, 8 zeros. I get 1, 8 zeros. So for every hour on the sun, sorry, for every hour on the Earth, the sun experiences 1.000000 2.5 hours. I think I missed a couple of zeros in there. Okay. Is the sun at rest? Okay, it's moving around the center of our Milky Way galaxy. So let's put the solar system's speed into the time dilation equation. We get 2.1, scientific notation button 5, divided by 3, scientific notation button 8, squared, 1 minus that, square root of that, 1 divided by that. And I get 6 zeros and a 245. So for every hour that we experience, the Milky Way galaxy experiences 1.0000245 hours. Time is moving slightly faster on the Milky Way galaxy than for us, at the center of the Milky Way galaxy. Okay, let's go faster. UBC has a particle accelerator. It's called Triumph. If you ever get a chance to take a tour, take a tour. It's very cool. When it's running, there is a room where the magnetic field in that room is so strong you have to power off your phones, otherwise it'll wreck your phones. And it's strong enough that if you scatter paper clips on the desk, some of them will stand on end like this. That's how strong the magnetic field in the room is. It's both terrifying and totally cool. Anyways, they can get protons that fast. Okay, so let's put that in. 2.24, scientific notation button 8 divided by 3, scientific notation button 8, squared, 1 minus answer button, 0.44, square root, answer button, and then 1 divided by answer button. And I get, for every hour the protons experience, the people in the particle accelerator room, Emma, experience how many hours? It's almost 1.5 exactly. They have to take that into account, the fact that time for the protons is moving differently. If they did not, all of their estimations for how long it will take the molecules to decay and all of their radioactivity estimations, that don't work. They have to take into account. Otherwise, the numbers don't match. I'll skip muons at CERN. They're cool, but I can see you're getting a little restless. Let's look at Stanford University can get electrons going 2.9979 times 10 to the 8th. How much is time dilated for those? 2.9979, scientific notation button 8, divided by 3, scientific notation button 8, squared, 1 minus that, square root of that, 1 divided by that. And you get 26.7? So for every hour of existence the electrons experience, the workers go through over 1 day. And again, they have to take that into account when they're doing their research calculations. If they're looking at, how fast are these electrons decaying? How fast are these electrons combining? The times don't match unless they take that into account. Mr. Dueck? Yes, Nicholas. Could you show me a video that explains or illustrates time dilation in 10 seconds? I can. This is a physics joke. Are you ready? Here you go.
This video would be 10 seconds long if you watched it while your computer was whizzing past you at 87% the speed of light.
So that's a physics joke, because how long is this video in our reference frame? How many seconds was it? 5 seconds. But if it went whizzing past you at 87% of the speed of light, you would see the video moving slower. For you, it would take 10 seconds in your reference frame. You would see the people on the spaceship seeming to move much slower. They would be moving half the speed of a normal person, because time would be slower for them relative to you. Would the people on the spaceship notice anything? No, because they're inside the spaceship. For them, time is moving at their rate. So that's a physics joke. Ha ha ha, Mr. Okay, fine. So we've been talking about time travel. How can you travel through time? This is not on your test, but I'll give you 3 easy ways to travel through time and then 3 more complicated ways. This is from the YouTube channel Minute Physics, one of my favorite YouTube channels.
Time travel can be complicated and complicating, so let's ignore all the paradoxical stuff and talk about a few simple ways that you can time travel without leaving your home. First, do nothing.
You're all traveling through time right now. Ready? About 1 second just elapsed. You moved about 1 second into the future. You're baked into time. And so you're all technically time travelers, but I know that's not what you mean when you think time traveling. You want to be moving through a different time relative to somebody else. Fair enough. But for what it's worth, you're all traveling through time.
You're already traveling through time. I mean, here you are, 15 seconds into the future since the start of this video. Easy, right? The point is, we're all always traveling forwards through time. But that's boring time travel. What's interesting is time travel relative to other people. To do that, start walking, and you'll travel through time relative to someone standing still. We've known for over a century that time and space are really just 2 components of a single space-time, and the faster you move, the slower time will pass for you. If you take a walk around the block, you'll be 3 femtoseconds younger than your friend who stayed home.
We couldn't calculate that. We tried with that 2 meters per second. It was too small for our calculators. But if you use a long number calculator online, you'll get about that kind of an answer.
Except in order to walk around the block, you had to stand up. You're now further from the Earth, and so gravity is a tiny bit weaker for you, which means you're traveling through time relative to your friend who's sitting down. That's right, more gravity makes time slow down too.
Gravity also affects time. If you saw the movie Interstellar, the time traveling in that movie was based on black holes distorting gravity, and that's a consequence of general relativity. It turns out accelerations and gravities also affect time, but differently than when a is equal to 0.
If you stand up for a minute, your feet will age 10 femtoseconds less than your head. On the other hand, GPS satellites high in orbit experience less of Earth's gravity and thus travel noticeably faster through time than we do, which is why their clocks are calibrated to run slow. But maybe you want to time travel more than a few femtoseconds. Get ready for your head to start spinning.
So here is some more exotic ways to travel through time.
The universe. Because if the whole universe were spinning calibrated to run slow. But maybe you want to time travel more than a few femtoseconds. Get ready for your head to start spinning. The universe. Because if the whole universe were spinning really fast, general relativity predicts there would be time loops all over the place. Moving along one of these loops, you'd always feel like you were moving forwards in time, but overall you'd loop around and travel back to a time and place in your own past. It's a little like how you can keep moving forwards on the Earth, but Earth's curvature brings you back to where you started. Unfortunately, our universe isn't spinning. Maybe it would be easier to build an infinitely long, super dense spinning cylinder, which would also curve space-time enough to create a time loop. The problem, of course, is how do you build something that's infinite in size? Maybe you could just make it really, really big? No. If you tried to squeeze this time machine into finite space, you'd need negative energy, something nobody knows how to create, to make it work. Otherwise, you'd end up with a black hole. Wait, but what if instead of a black hole, we built a wormhole? Wormholes are hypothetical but not physically impossible bridges through space-time, shortcuts that can instantaneously connect two different places and times in our universe. If you had a wormhole, you might be able to use it to travel into the past or the future. The problem is that no one knows how to build a wormhole, or once you've built it, how to keep it from collapsing. As Sean Carroll has eloquently written, keeping wormholes open requires a form of negative energies. Nobody knows how to make negative energies, although they occasionally slap the name exotic matter on the concept and pretend it might exist. Well, that's too bad, but as a consolation, welcome to the future. Almost 3 minutes have passed since the beginning of this video, and we now have personal jetpacks.
So 3 easy ways, 3 more complicated ways. All of that we've done so far, Ange, was just kind of a setup. Now let's get to the actual lesson. Pick your pencils up, turn your brains on. You want the green sheet open to the back page. It turns out another consequence of special relativity, Kate, it's not just that time is different for objects moving at different speeds. It turns out it says this: the length of an object will be measured to be shorter when it's moving than when it's at rest. But this shortening will only be seen in the direction of its motion. What? Look up. If you were to go zipping past the Earth near the speed of light, and if your speed was in that direction, that's what you would see. If you were at rest, the Earth would look like its normal Earth, but as you started to move faster and 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 faster, the Earth in your universe would get shorter. And it isn't just that you would see Earth look shorter. No experiment that you could come up with would behave that it wasn't actually that skinny. It would be that skinny in your universe. If you had a big tube, because you were some kind of giant, and that tube was this wide, you could slide it over the Earth, and the Earth would fit in that skinny tube in your universe. Just fine. I'm not going to prove this equation with you, but here's how it works. Turn the page. Let's suppose the length of an object when it's standing still is L0. If you're standing still, how fast are you traveling as a number exactly? So are you saying I can remember that L0 is when I'm at speed 0? Okay. The theory of relativity says that the object's length L, its relativistic length, when moving at speed v will be measured to be, and here is the equation. You're not dividing by the square root, you're multiplying by the square root. Or if you want to use that Lorentz factor abreve, you can write it like this: L equals L0 times that gamma thing, because that gamma thing is the abreve for the square root of 1 minus v over c all squared. I'm willing to bet all of you can figure out how to type this into your calculator, because it's kind of the same stuff we've been doing. What we really need to know is which one is L, which one is L0. So L0 is the original length at rest, and you can put in brackets at v equals 0. So you can remember L0 in 2 different ways. You can either, Brandon, say L0 is the original length at rest, or you can say L0 is the original length at speed 0, L0 speed 0. And then L is what we call the relativistic length when moving. Let's do an example. Let's imagine that we have a meter stick, this one, and it's whizzing past us to your right at how fast in example 1? Okay, at 99.5% of the speed of light. Let's pretend you have Superman eyes, you can actually see it. because if it was moving that fast, our human eyes would not even register it. But let's pretend we have Superman eyes, we can see it. Okay? How long would we see it to be? That's a good question. So example 1 says, how long would a meter stick appear to be if it was moving past you with a speed of 99.95% of the speed of light? What's this question asking me to find? A length, L or L0? How do you know? Okay. Have we done one of these before? I don't know. Let's fall back on our default. Let's go L equals question mark. Sorry, I'm using capital L. L equals question mark. L0 equal, oh, ready boys and girls? Maybe this is too obvious. What's the original length of a meter stick at rest? I'll give you a hint. It's a meter stick. 1. Is that okay? Not a big shock. What's our speed? How would I write 99.5% of the speed of light? 0.995 c. Okay. Here's my length contraction equation. It says L equals L0 times that square root thingy. What do I need to get by itself? L or L0? Hey, it already is. Bonus. Yes. So it's going to be 1 times the square root of 1 minus 0.995 c all over c squared. Hey, Nick, do you see? Do you see? Do you see? What do you see? C's cancel. Get your calculator out. Try typing this in. What do you get? Do I need to multiply by the 1 in the front? Will that change the answer at all? So if you skip that step, I won't freak out, Cal. I mean, you can go 1 times, but really, it's just going to be the square root of bracket 1 minus 0.995 squared, close bracket. Type that in. Y'all get 0.099. You know what? I think that rounds off to 0.1 meters. What that means, Daniel, is if you saw this meter stick go whizzing past you, to you, it would only be, where's the 0.1, Mr. Newick? There's the 10 cent. It would only be this long. The writing would be really, really squooshed together. The writing would look long and skinny. Okay? And in your universe, even though at rest this meter stick is 1 meter long, in your universe, while this was moving, you could cover the entire meter stick up with your hand because it's small enough to fit behind your hand. That's getting a little weird, but cool. Is that all right? Let's do another one. Example 2, an 85-meter long spaceship passes you at 2.23 times 10 to the 8th meters per second. How long does the spaceship look to you? Is this asking us to find L or L0? Well, it's asking how long it looks to us. Are we moving or are we at rest? Is the spaceship moving or is the spaceship... I think this is... Because the spaceship is moving relative to us, I think this is asking us for the relativistic length, how long it appears to us. I think this is asking us to find L, which means, Zach, what's L0? Is that a length? What are the units next to that 2.23? How do you know? Is it worth memorizing what units go? This is part of why at the beginning of the year I told you, as much as I hate memorizing stuff, memorize the units. It helps you figure stuff out. Is that okay, Zach? What's that 2.23 times 10 to the 8th, Zach? Is this going to be a do you see, do you see, do you see, what do you see? No, but we practiced a bunch of these too. Okay, so we want to get the L by, it already is. L is going to be L0 times the square root. It's going to be 85 times the square root of 1 minus 2.23 times 10 to the 8th all over 3 times 10 to the 8th. Don't forget the squared. I'm going to see if I can type this in one step. It's going to be 85 times square root button 1 minus, oh, I got to do a bracket inside the square roots probably. 1 minus bracket 2.23 scientific notation button 8 divided by 3. Scientific notation button 8. Close off the bracket. Don't forget the squared. Close off the square root. I think that's right. Will I perceive the spaceship to be longer or shorter? Shorter. So I should get an answer less than 85. And I get 56.9. Example 3. Suppose a spaceship is 100 meters long when stationary. When what? You know what? That's L0. I wrote it really small, but that 100 is L0. When it moves past an observer, the observer measures the spaceship to be 25 meters. You know what? That's L. Brea, what's example 3 asking me to find? How fast? Oh, on the back of your green sheet, is there a V equals equation that has L's in it? Brea, can you read me that one, please? I'll give you a hint. V equals, and I think there's a C. Sorry, C square root of what? 1. I choose to write that as L over L O all squared because it's just less typing on my calculator. Okay. Let's plug in the numbers. First, let's give it as a percentage of the speed of light. How would I do that? I'm just going to leave the C as a C, and I'll end up with some decimal C, which is a percentage. So I'm going to go C square root of 1 minus 25 over 100. Don't forget the squared. Square root of bracket 1 minus bracket 25 divided by 100. Close off that squared. Close off the square root. And I get, do you get 0.968245836? That there? I'll go to, because we're being pretty precise, I'm going to go to 4 sig figs. I'm going to write this as 0.9682. 0.9682 C. What percent of the speed of light is that? 96.82% of the speed of light. Okay. How would I convert this to meters per second if they asked that? On your take-home quiz, I asked for both. One I said, give me V as a percentage. One I said, give me V as a meters per second. How would I convert this to meters per second? Yeah. What will I do with that 3 times 10 to the power of 8? Times what? More nouns, less pronouns. Yes. Okay. Just replace the c with a 3 times 10 to negative 8. So it's going to be 0.96. That's terribly messy. Times 3 times 10. Did I say to negative 8? To the 8th. I'm going to use my answer button. So I'm not going to use the 0.968. I'm going to answer button times 3 scientific notation 8. In meters per second, I get 2.905. I'll go to 4 sig figs. Meters per second. That is pretty close to 96.82% of the speed of light. So weird stuff happens with length. We're going to do one more, example 4. I like example 4, I like example 4, I like example 4. Example 4 is a nice question. A certain star is how far away? Is it? Let's find out. How long would it take a spaceship traveling at 95% of the speed of light to reach the star A, as measured by stationary observers on the Earth, B, as measured by observers on the spaceship, and then C asks, what is the distance traveled according to the observers on the spaceship? We did one like this last lesson with Proxima Centauri, where I talked about how this is how a space mission would work, but let's do it again. Brandon, what does A want me to find?
L.
Sorry?
L.
I disagree. I know it says how long, but keep reading. I think this is asking for time, is it not? I think this is saying how much time. You agree with me now that I've said that? Okay? Okay. In part A, has the spaceship started moving yet? No. So we're not going to use Einstein's equations. We will in part B, but we're just going to use this. D equals VT. We're going to get the T by itself. Why is that going to work? Nick, what did we say that A was in this unit? Okay, you're not looking at your phone or anything foolish, right? No. Okay. Let's get the T by itself. It's going to be D over... So, Brandon, that must mean they gave me a distance that the spaceship is traveling. How far is the spaceship traveling? 15.6 what? 15.6 what? I want units. 15.6 what? I want the... Read it. 15.6 what? Light years. Is that a measure of distance? Yes. Don't think that's time, even though it has years in it. That's a distance. So I agree with you. 15.6 light years. What's our speed?
0.96.
So our spaceship relative to Earth is going to go 15.6 light years divided by 0.95 c. Hey, the c's cancel. I get an answer in years. 15.6 divided by 0.95. Do you all get that Earth thinks this is going to take 16.4? That's relative to the Earth. Will it take longer than that or shorter than that for the astronauts? Because they're moving. Okay. So, Reed, what does B want me to find then? T0. How would I get the T0 by itself in our time dilation equation? How will I move the square root over? Why? Because what's the square root doing to t0? So I'm going to write it like this. T times that gamma thing, because that's the abbrev for the square root of 1 minus v over c all squared, and I'll abbrev whenever I can. Read, what's time? Our answer from A, and I'm going to use my answer button, okay? I'm going to write 16.4, but I'm hitting my answer button here, times the square root of 1 minus 0.95c over c all squared. Hey, do you see? Do you see? Do you see? What do you see? Okay. So if you go answer button times square root of bracket 1 minus 0.95 squared, close bracket. How much time will elapse on the spaceship? I get 5.13. Is that right? Someone else? I might have made it wrong. Am I right? I see people nodding. Okay. Cool. Danica, what's D you want me to find? Keep reading. Traveled by who? Okay. Traveling for the spaceship. Okay. So draw a line down the middle of the page. There's actually two ways that we can do this. The first way is we can go D equals speed times time. What's A? Einstein didn't know how to deal with acceleration yet, so A was equal to? Okay. What's the speed that the spaceship is traveling at, Danica? 0.95c. And for how long is the spaceship traveling? We're going to put T0 in here. So I'm going to write 5.13, but what button am I going to press on my calculator? And of course I am. So try that. Oh, by the way, notice, Danica, if I do that, if I put the units in for the 5.13, see, I do get light years, which is a distance. Ha 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 ha. So, okay, I'm going to go 0.95 times answer button. And I get 4.871098, I got 4.87. How far away does Earth think it is? How many light years? But when we do the experiment, how many light years do we find it actually is? And if they went faster, they would find the distance was even shorter. Even distances aren't consistent. Yeah. Oh, I wrote 9.7, not, what was it? 8.7. Thank you. There's another way I could have done this. I could have used my length contraction equation. Write that down. We're going to find the relativistic length that the spaceship discovers. What was L0? That was the original length at rest. What was the original length that Earth measured to this star when the Earth was at rest? Times the square root of 1 minus 0.95c over c. Don't forget the squared. Do you see? Do you see? And I want you to notice what happens here. This is kind of cool. If I go 15.6 square root of bracket 1 minus 0.95 squared, close bracket, I also get exactly 4.871098,439. You can find the spaceship distance using either of those methods, but the fact that I got the same answer for both says to me, because I never derived this equation, I didn't prove the length equation, I think the length equation's right, because we got it with the time dilation equation one way, which I did prove with you. Okay. I know I've been talking for a long time. I'm almost done. So, what does this mean for an object that travels at the speed of light? Like a photon. You know what? Let's take our length equation. 1 minus... How fast does a photon travel at the speed of light? So I'm going to put a letter C in where the V is. So, Lena, what's 5 divided by 5? 1. What's 10 divided by 10? What's C divided by C? What's 1 squared? What's 1 times 1 in your head? What's 1 take away 1? 0. What's the square root of 0? How much length do photons experience as a number exactly when they're traveling through the universe? So, you may have looked out late at night, Lena, and looked at the stars, and you may have thought to yourself, oh, it took those photons thousands of years to reach me. How much time did those photons experience? We did this last day as a number. How much time did those photons experience? Nothing. And you may have thought, oh, and they traveled across the galaxy, across the universe to reach me, traveling vast distances in vacuum of space. How much distance did the photons travel as far as they're concerned, Lena? Nothing. So again, I did this with you the other day. I'm going to create some photons, and for you, in your reference frame, those photons just winked into existence. But because they don't experience time, they're seeing the Big Bang and the end of the universe. And not only that, because distance is irrelevant for them, they're seeing everywhere in the universe right now, too. Light is special. Just saying. Light is pretty cool. You've been very patient. Your homework is you want to get the take-home quiz done for sure. I'm going to have a much shorter lesson tomorrow. We're going to mark the take-home quiz, and then we're actually done the unit. We're going to press pause for a day. I'm going to give you another take-home quiz and a study guide. Right now, I'm thinking our test on relativity will be next week, Monday, Tuesday, Wednesday-ish, and we'll kind of decide Thursday, Friday what works best for you folks.